Good morning, everyone, and welcome to today's lecture. Well, we have taken some steps forward, and we are into the last part of your motion in two dimension. So we will finish that part. This part is known as circular motion. I think we have already done some problems in circular motion, but now again we see this circular motion in a different light. How we can solve problems of circular motion in a more easy way. Now, first of all, to begin with, we must understand what is a circular motion. So, can you tell me what is a circular motion? Can anyone tell me what is a circular motion? What do you understand by circular motion? Yes, tell me fast. What do you understand by the concept of circular motion? Anyone? Yes, beta? You're not audible properly. If any particle moves on a circular path or circular track, that is circular motion. But instead of saying it in this way, we can say it in a different way. If a particle moves such that, if a particle moves, and I hope everyone is writing, if a particle moves such that what? Its distance from a fixed point its distance from a fixed point remains same, then that motion is known as circular motion. What is that fixed point known as? That fixed point is known as the center of the circular motion. Center of CM, circular motion, and that fixed distance is known as the radius of circular motion. Anyone knows any circular path, any circle has a center and it also has a radius. The fixed point is known as the center and the fixed distance is known as the radius. So if I draw it in this way, if any particle moves like this, here is the center O and the radius of this circle is R, and there is a particle moving such that at some point, at some time it is at A, at some time it is at B, then C, then D, then E, then F, then G, then H, and so on. If it is moving like this motion would be known as circular motion. Do we understand this? Yes or no? Simple, it's moving on a circular path. This motion is known as circular motion. No questions asked, no answers given. Now, how are we going to find out where the particle is at any point in time? How do you know its position? Now, one way of knowing its position is to, okay, how do I know the position of a particle following circular motion? How can I find the position of this particle? How can I find the position of this particle? What type of motion is this? Is this motion in 1D, 2D or 3D? Tell me that, fatafat. Is this 1D, 2D or 3D? This motion that is happening, is it 1D, 2D or 3D? Fast, fast, fast. You have to complete this topic quickly. 1D, 2D. No one knows? Huh? No one has any idea what type of motion is this? Can't hear you. 1D. You can signal with your fingers. 1D or 2D or 3D. 1D. 1D. Everyone saying 1D. This is motion in one dimension. Yes or no? Or is it 2D? Or is it 3D? No one knows? Okay, that's good that no one knows it. This is an example of motion in two dimension because both the x and the y coordinate of the particle are changing. So one way of telling you the position is I draw my x-axis, I draw my y-axis. At any point, if the particle is here, at any point if the particle is here, I can tell you its x coordinate. I can tell you its y coordinate. So this is the way I can tell you where this particle is. I can draw a vector also connecting this point O to A. I can call it the position vector of the particle. This is one way of telling you what is the position of this particle in terms of X and Y. Yes, sir, is the mic working?
Sir, am I audible?
Yes, sir, you're audible, but when students talk, I can't hear anything. Okay, so this is one way of telling you the position of this particle. I tell you the x coordinate, I tell you the y coordinate. But instead of doing it this way, we can do it in a different way. And what is the different way? We have talked about the radius of this circle and the center of this circle. So instead of telling you the x and the y coordinate, there is a different way of doing the same thing. I must not take this. This diagram is not good. Just erase it. So instead of telling you the x and the y coordinate, what I'm going to do is to say the same thing in a different way. How can I say it in a different way? Same thing said in a different way. This is my origin, which is also the center of the circle. This is your x-axis and this is your y-axis. Now, instead of telling you if the particle is at point A, instead of telling you the x coordinate and the y coordinate, what I'm going to tell you is, I'm going to tell you the radius of this circle r. So you know where the particle is, how far it is. And then I'm going to tell you this angle theta that it makes with the positive direction of x-axis. So I'm going to tell you two things. Here, if I write the position of point A, I will write the position of point A as x comma y. I am telling you the x and the y coordinates. Here, if I tell you the position of particle A, I will tell you in terms of r and theta. Such type of nomenclature is known as the polar coordinates. This is known as the polar coordinates. And this one is known as the rectangular coordinates. So instead of telling you the x and y, the Cartesian or the rectangular coordinates, I can tell you r and theta. R is the radius of the circle, theta is the angle it makes with positive x-axis. Remember, this theta should be the angle that it makes with the positive x-axis. Now, this theta could be in this direction. Let me make this with a different color. This theta could be in this direction. Then this theta will be known as positive theta. This theta could be in this direction from the x-axis. Then I call it as negative. Basically, anti-clockwise. This is anti-clockwise. Anti-clockwise angles are taken as positive and clockwise angles are taken as negative. I told you that before also. Yes or no? Did I tell you? That is the sign convention we use. Anti-clockwise angles are taken as positive and clockwise angles are taken as negative. So instead of telling you x and y, I can tell you r and theta. This theta is known as the angular position of the particle. This theta is known as the angular position of the particle. So the first thing that we are going to study is number one, the angular position of the particle. The angular position of the particle, and it is given by the angle theta. And what is this angular position of the particle? It is the angle it makes with positive direction of x-axis. Angular position of the particle is the angle it makes with the positive direction of x-axis. What type of quantity is angular position? It is a scalar quantity. Its SI unit is, remember, radians because it's an angle, and the dimension it has, it is a dimensionless quantity. It has got no dimensions, but it has a unit. Remember, angle is only quantity which has no dimension, but it has a unit. Do we remember this? Yes or no? This is known as angular position. Do we understand this? Yes or no? Angular position. Now, when this particle is going to move in a circular path, its angular position is going to change. At some point, as you can see, it will be at point A. At some point, it will be at point A. At some time, it will be at point B, then C, then D, then E, F, and so on. The distance r remains same, but the angle changes. Whenever this angle changes, we can call it change in angular position, or we have the next term for it, which is known as angular displacement. We have got the next term for it, angular displacement. Angular displacement. Now, how do I denote this term angular displacement? It is known as delta theta. Delta means change, theta means angle. So how do I find this angular displacement? This is change in angular position. This is nothing but the change in its angular position. That means your angular displacement delta theta will be theta 2 minus theta 1. Theta 2 is the final angular position. Theta 1 is the initial angular position. So you can write it like this, or you can also write it like this, theta f minus theta I. Is everyone understanding what we are doing here? Yes or no? Yes or no? Now, what type of quantity is angular displacement? Now, here you have to understand something which might be a bit different than what we have seen. bigger angular displacement, if the angular displacement is big, 10 degrees, 15 degrees, 20 degrees, bigger angular displacement, or if I write it, delta theta, if the angular displacement is big, more large, then it is taken as a scalar. It is a scalar quantity. Important, you have to understand. Whenever I say delta theta, this delta theta change in angular position is a bigger quantity. It means change is big. That is a scalar. Smaller angular displacement, a very small angular displacement. So I write it as d theta. Do you remember this d theta? dv, dr, dA, this is d theta, small. This d theta is a vector quantity. So I write it as vector. This d theta, this small angular displacement, this is a vector quantity. So it is written as a vector. Do you understand this? Yes or no? Small angular displacement is a vector. Big angular displacement is a scalar. The SI unit is same as the SI unit is same as radians. And you must remember that 180 degrees is pi radians. We have seen this relation, yes or no? 180 degrees is pi radians. Do we remember this? Okay. Have you noted this down, everyone? I'll give you 2 minutes to note it down. Let me know once you're done. Have you noted it down, everyone? Yes or no? Okay. Now, as soon as we have introduced these two terms, angular position and angular displacement, if I would just take this angular thing out from both of these, if I just take this angular thing, it becomes position and displacement. Have you heard this term, position and displacement? Have you heard this term, position and displacement? Whatever we are going to study in circular motion is taken from what we had studied previously in motion in 1D and 2D. In 1D, we had a term known as position vector. Do we remember this position vector? That was a vector, therefore it was called as vector. Otherwise, it was position. It was telling us the position of the particle. So this theta in circular motion is same as angular position. The only thing is that was vector, this is not a vector. This angular displacement is the change in angular position. This is exactly same as what? Angular position is same as position vector. Then what is angular displacement same as? Angular displacement is change in angular position. So what is this same as? It is same as the displacement vector. So angular position is telling us the position of particle in circular motion. Position vector was telling us the position of the particle in your motion in 1D and 2D. Angular displacement tells us the displacement of the particle or the change in angular position. The original displacement delta r was also telling us the displacement. It was in 1D, 2D motion. This is in circular motion. So whatever we are going to study in circular motion is same as what we had studied in your linear motion or motion in 1D and 2D. We have studied position vector, we had studied displacement vector. What else did we study? That is the third thing. Average angular. Can you complete the sentence? Average angular. What is the next thing we are going to study? Average angular. No one knows. Average angular velocity. Average angular velocity. Omega in a dabba. Omega in a dabba. What is this average angular velocity? It is angular displacement. It is angular displacement divided by total time. Angular displacement divided by total time. So I can write average angular velocity as delta theta by delta t. Average angular velocity. What is it same as previously? Had we studied any term like this? Yes or no? What was that term that we studied? Anyone of us remembers it? Do we have a mic that we can use to speak? Anyone of us remembers? What is this term same as? No one? Okay. This is same as average velocity. Average velocity was total displacement divided by total time. This is angular displacement divided by total time. Remember, this is a scalar quantity. This is a scalar quantity. The SI unit is radians per second. Dimension is 1 by t, or instead of writing it as 1 by t, I will write it as t raised to the power of -1. I'll give you 2 minutes to note this down. I hope we are able to recollect something that we had done previously. If not, we can go back and see what terms we were talking about. 2 minutes. Please tell me once you are done.
Completed, sir.
Okay, well done. Then comes the next quantity. What is the next quantity that we are going to do? What is the next one? First one was angular position. The second one was angular displacement. The third one was average angular velocity. What is the fourth one? No one?
Angular acceleration.
No, it is instantaneous angular velocity. Instantaneous angular velocity. Instantaneous angular velocity represented by omega, and this is a vector. Instantaneous angular velocity. This is a vector quantity. What do you mean by this? This is the angular velocity at any instant. If you want to find out what is the angular velocity now, that is known as your instantaneous angular velocity. How do I find this instantaneous angular velocity? It is d theta by dt. As soon as you understand that this is d theta by dt, you can also write this in this form. It is the rate of change of angular position with time. It is a vector quantity because small theta, d theta is a vector. SI unit is same as radians per second. I don't need to write it. And the dimension is same as t raised to the power minus 1. Which quantity is this quantity similar to? Instantaneous angular velocity. Which quantity is this quantity similar to? Do we recollect it? Yes or no? Okay, I must change my statement now. I always used to say that the NEET students are brighter than the JEE students.
Instantaneous velocity, sir.
See, my faith has been restored. It is instantaneous velocity. It is same as instantaneous velocity. Great. Instantaneous angular velocity, omega vector, is same as velocity vector. Now both are vectors also, so we don't have to worry about. There are different types of vectors, but we'll not get into that. Instantaneous angular velocity. Now, what is the next thing that we are going to do? What is the next term that we are going to study? Huh? What is the next term? The next term is known as uniform. There it was uniform motion. Velocity remains constant. Uniform motion, velocity remain constant. Here it is uniform circular motion, which is known as UCM. Uniform circular motion, which we call as UCM. Now, what do you mean by this UCM? If the angular velocity remains same or constant, the motion is known as uniform circular motion, and it is same as your uniform motion in your linear motion where the velocity was constant. If the angular velocity is constant, it is known as uniform circular motion. So in this case, what would happen, bacha? Your average angular velocity will be same as instantaneous angular velocity. The magnitude I will have to write because one is a scalar quantity and other one is a vector quantity. So I will write it as, it will be same as the magnitude of angular velocity. Remember, here we might not be using vector sign for angular velocity. We will be using plus and minus for angular velocity. And I always told you, if it is anti-clockwise, it will be taken as positive. It is clockwise, it is taken as negative. In motion in one dimension, forward was taken as positive and reverse was taken as negative. Up was taken as positive, down was taken as negative. In this particular topic, anti-clockwise will be taken as positive and clockwise will be taken as negative. Do we understand this? Yes or no? UCM, uniform circular motion. It's a very important type of motion which will be coming many times in many topics. Whenever we have this uniform circular motion, we have omega constant, and I will not write omega as a vector now because I'll be taking plus and minus. I just don't want to overcomplicate things. If omega is like this, it is plus. If omega is like this, it is minus. Now, as soon as we hear about UCM or uniform circular motion, few terms are going to come. The first one is known as time period of UCM. Now, you must have heard about this term time period denoted by capital T. Tell me what is time period of a uniform circular motion. Give me examples of uniform circular motion first. And you will see a lot of examples in your day-to-day life of uniform circular motion. Can anyone give me an example of a uniform circular motion? If you understand, if you can give me an example, it will be easier for you to understand this concept of time period. Yes.
Earth rotating on an axis, sir.
Yes, beta.
Earth rotating on its axis, sir.
Earth rotating on its axis, its angular velocity is constant, right? Anything else that you can think about? Earth rotating on an axis is very correct. Your fan right now, it is moving at a constant angular velocity. This is also uniform circular motion. The motion of the tip of your clock का seconds वाला hand, uniform circular motion. Hour वाला hand, uniform circular motion. Minute hand, uniform circular motion. Revolution of earth around the sun, uniform circular motion. Motion of moon around earth, uniform circular motion. Not actually, revolution of earth around the sun is not uniform circular motion because it is elliptical path. Motion of a pendulum, so pendulum moves like this. Now, if you understand uniform circular motion, what do you mean by time period of a uniform circular motion? What do you mean by time period of a UCM? Anyone? Its angular velocity is constant, so it would always complete one revolution in a fixed time. So this is time taken to complete. Time taken to complete what? Time taken to complete what? One revolution. When I say one revolution, I mean an angle of 2 pi, or if you want to understand in degrees, but never write it in degrees. In degrees, it is 360 degrees, but we never use degrees. We always use radians, so always it is 2 pi. Time taken to complete one revolution. In a UCM, time period is always constant. Time period of the rotation of a second hand is 1 minute. In 1 minute, it completes 360 degrees. Time period of rotation or movement of a minute hand is 60 minutes, 1 hour. In 1 hour, it completes one circle. time period of a hour hand of a watch or a clock, not a watch, clock is 12 hours. It completes one circle in 12 hours. That is known as the time period. Time taken to complete one revolution. In one revolution, it moves an angle of 2 pi and not 360 degrees. We don't call it in degrees, we call it in radians. Do we understand this? Yes or no? Can I have raised hands from everyone in the class? Boys, are we there? Or still hanging around somewhere? There in the class, everyone? Okay. What is the SI unit of time period? We don't have to think much about this. It is time. So SI unit is second. Now, as soon as we hear about the time period, the second thing automatically comes in our mind, and that is known as frequency. Frequency denoted by the letter F. What do you mean by frequency? Anyone? You must have heard about these terms. It is number of revolutions in 1 second. Number of revolutions in 1 second. For a uniform circular motion, this is also constant. The frequency is constant. Then we have a relation that relates time period, omega, and F. What is that relation? Anyone knows that relation? Time period is 1 by F. Have we seen this relation ever? Time period is the inverse of frequency. Since we understand that time period is the inverse of frequency, I can write the SI unit is hertz and dimension is t raised to the power of -1. Time period is 1 by F. Do we understand this? Yes or no? Time period is 1 by F. This is the first formula that you must remember. The second formula is omega, your angular velocity is 2 pi by t. Why it is 2 pi by t? The total angle that is turned is 2 pi. It moves the total revolution in t seconds. Therefore, your angular velocity in this case becomes 2 pi by t. You can also write, because t is 1 by f, you can also write omega as 2 pi f. Do we understand this, what I'm writing here? Omega is angular velocity. Do we understand this? Omega is angular velocity. Remember these three formulae because they are going to come in almost everything that we are going to do from now onwards. Whether it is simple harmonic motion, whether it is wave optics, everywhere this is going to come. Remember this. Omega is 2 pi f. Omega is 2 pi by t. Omega is 2 pi f. Now, omega is known as angular velocity, but in some cases, you will see in when we go ahead, we will call omega by a different name also. Remember, right now, in uniform circular motion, this is angular velocity. But in coming days, we are also going to call it by a different name. We are going to call it angular frequency also. So angular frequency and angular velocity actually formula wise, concept wise are similar, but they are used in different scenarios in different way. Why it is known as angular frequency? Well, the simple reason I can give you, F is frequency. F is frequency. F is frequency. Two pi is angle. If I multiply angle with frequency, whatever I get is known as angular frequency. So that is how we can understand that omega is also known as angular frequency in some cases. Do we understand this? Yes or no? Let us complete the definitions today so that we can move ahead with the questions in the next class. What is the next term that is going to come? Let us finish the terms. Now, we have done angular position, angular displacement, average angular velocity, and instantaneous angular velocity. And we have seen that if the velocity or angular velocity is constant, the motion is known as uniform circular motion. What happens if the angular velocity changes? Who is going to change angular velocity? What changes angular velocity? So comes our next term, term number 5. What is the term number 5? What is the term number 5? Average angular acceleration. Average angular acceleration denoted by alpha. It is a vector with a dabba meaning average. Now what do you mean by average angular acceleration? It is total change in angular velocity divided by total time. Total change in angular velocity divided by total time. I can write the formula now. Average angular acceleration will be omega 2. It is a vector minus omega 1. It is also a vector divided by t. What does this term remind you of? Average angular acceleration. Does it remind you of any term that we have done previously? Yes or no? No, yes. This is same as average acceleration. What type of quantity is this? This is definitely a vector quantity. The SI unit is radians per second square. The dimension is t raised to the power of -2 because radian does not have any dimension. Average angular acceleration. That is the fifth term in the process. Have you noted it down, bacha? Yes. Then comes the last term. And what is the last term? The last term, the sixth term is instantaneous angular acceleration. Simply alpha vector. What is this instantaneous angular acceleration? This is the angular acceleration at any instant. At any instant, what is your angular acceleration? That is known as your instantaneous angular acceleration. Whenever someone talks about what is your angular acceleration, he's talking about your instantaneous angular acceleration. So the formula of instantaneous angular acceleration becomes, oops, why I'm writing theta, d omega, small change in angular velocity divided by small time. So you can also call it the rate of change of angular velocity with time, rate of change of angular velocity with time. An important note that you must remember: if angular acceleration is constant, then if your angular acceleration is constant, then your average angular acceleration will become equal to instantaneous angular acceleration. Do we understand this? Yes or no? No, yes. Anyone understand this? Can I have raise hands from everyone? Pakka? Okay, have you written this down? Have you noted this down? Okay. Now, in most of the cases, the question that are going to come will be of uniform angular acceleration. So we can now write in 2 minutes quickly the equations of circular motion. Equation of circular motion. Remember, this is for constant angular acceleration. What would be your equations of simple harmonic motion? Simple harmonic, I'm saying. Equation of circular motion. If the acceleration is constant, what will be your first equation? Remember, whenever we are using this equation, we are using a sign convention. What is the sign convention that we are using? Anti-clockwise is taken as positive and clockwise is taken as negative. You understand the meaning of anti-clockwise and clockwise? So then if you take this convention, we don't have to take them as vectors, we can take them as numbers. What will be the first equation? First equation, omega 2 will be equal to omega 1 plus alpha t. What is omega 2? What is omega 2? It is the final angular velocity. Do we understand this? What is omega 1? Anyone can tell me what is omega 1? Initial angular velocity. Alpha is your angular acceleration and t is your time. If this is your first equation, what would be your second equation? Can anyone tell me? Fatafat. I hope this equation reminds you of something that we have already done many times. What would be your second equation of circular motion? Anyone? Okay, no one wants it. No one knows it probably. So this is a revision of what we are doing. Delta theta, which is angular displacement, will be equal to omega 1 into t plus half alpha t square. Does this equation remind you of something? Yes or no? Yes or no? Okay, what will be your third equation? Omega 2 square will be equal to omega 1 square plus 2 times alpha into delta theta. The equation number 4 will be angular displacement in nth second will be equal to omega 1 plus alpha by 2 into 2n minus 1. These are the equation of circular motion, and I hope they remind you of something that we have already done. Yes or no? Do we understand this? Everyone in the class, we understand this? So everything that we have done today is nothing new, but it is just a recap of what we have already done. Next class, we will see some questions based on this and wind up this small topic, which is known as circular motion. So till next time, tomorrow is Saturday. So we'll wind up this by Saturday so that on Monday we can start a brand new topic. That would be Newton's laws of motion. Take care. May God bless you all. Bye-bye. Any doubt, please ask me.